This is a supplemental piece to week 8 on longitudinal models. Specifically, we're talking about latent growth models, which is a kind of longitudinal model. It turns out they're not that much different from what you've already been exposed to, but let's talk about them for a second. These latent growth models can be estimated in 2 different ways. One in a multi-level model. I call it a style. It's just a one way of estimating them. An equivalent way is to estimate them with structural equation modeling. The 2 approaches look very different, but actually they're very similar. So let's start out with multi-level characterization of latent growth models. HLM, hierarchical linear modeling, that program is often used to estimate this. And the key is to think of these models as consisting of several different equations. Okay, so the first equation is at the child level. Let's suppose we have every child observed in a data set with longitudinal data, ECLSK, for example, where they're observed every year for the first 5 years of schooling, right? Almost the ECLSK way of data collection. And let's suppose we've got some sort of scaled cognitive score that's vertically scaled and makes sense when you compare cognitive scores for 5-year-olds and 7-year-olds and 9-year-olds. You'd expect these scores to be growing over time for most kids. And let's just suppose that we have this pattern of observed cognitive scores by age. All right, so the first level of the multi-level model is at the level of the child. And it's a very simple equation. Usually it's essentially a bivariate equation. Sometimes there are control variables, but usually no control variables, where a child's cognitive score at a particular age is some linear function. Let's ignore the quadratic term here. Some linear function of age. So some intercept plus B1 age. And as I say, sometimes the first equation is fit to a quadratic. It might even be a cubic, but it's at the individual child level. That's really what's key here. So to work with this a little bit, let's rescale age. Instead of running from 5 to 9, let's start at 0, 1, 2, 3, 4. All right, that's a little bit easier because the intercept, where x equals 0, becomes coincident with the very first observation of 5-year-olds. So if we are fitting this equation, the intercept becomes the point on this curve that corresponds to age 5, because it is 0, it's the intercept. Okay, so we fit this equation and we get an intercept. You know, let's suppose I made this actual point too close to the line. Let's suppose that the first point was down here. So that's the cognitive score associated with age 5. So this line that we're fitting doesn't have to go through this point, doesn't have to go through any of these points. It just has to be the best fitting line through all the points. So the constant is not the first point, it's the projection of the best fitting slope back to x equals 0, which is age 5. So we're running this equation and we get this constant term for everybody, and then we get a slope. We've seen this before. So slope is B1. And again, we're ignoring the quadratic here. So that's the first level. It's just very simple. You run a bivariate regression on every single child in the sample, and you get an estimate of an intercept for that child, and you get an estimate of the slope for that child. So those pieces of information, the intercept and slope, then become dependent variables in the next two equations, right? So this is at the individual child level, but now we are at an aggregated level, and maybe it's a school, maybe it's a population. You want to aggregate up to the entire sample, and you want to have a regression where every single A that you estimate here, in other words, every single intercept is explained by some set of independent variables of interest. And then every single slope, B1, is explained by those same, or it could be a different set of independent variables of interest. Okay, so as we'll talk about more explicitly later, this is kind of a change equation, right? A slope is just kind of a measure of change over the 5 years, and you're predicting it by some independent variables. So it's not that unfamiliar. It's just unfamiliar because it's put into this multi-level model. But in order to get the measure of change, you're running this first level equation at the child level to get the best fitting slope. And by the same token, you're getting the best fitting intercept when you're predicting the intercept. Now, you can complicate this with a quadratic instead of a linear equation. You know, in this case, it is pretty linear. It's hard to imagine a parabola that might fit the data better. It might fit a little bit better. But everyone, if you fit a first level equation that's quadratic, every child gets a quadratic fit for him or her. And then you take the intercept, you take the linear term, and you take the quadratic term, and have 3 equations instead of 2 equations below. I always have trouble with quadratics in this kind of context. You know, I think it's true that for a population of kids, you tend to get cognitive scores increasing at a decreasing rate in the early grades. And so it's not really linear, and you might fit a quadratic to every child. And I think what fools people is that what might be true for a whole population of kids, in other words, the relationship is a quadratic, it's not exactly linear, gets very, very dicey when you're fitting a quadratic to every single individual child, right? So, you know, it's not the case if you actually look at data, you can look at ECLSK data, that pretty much every child has kind of a quadratic, and you've got different curvatures to the quadratic, different slopes to the quadratic. But in fact, things are much more chaotic than that. You've got kids bouncing all around. And I keep thinking about that case where we were looking, remember, at task value, that component of motivation in a different data set from ages 10 to 15, right, across middle school, roughly. And, you know, for the sample as a whole, you tended to get a declining task value, motivation declines. But remember when we tried to find the best fitting quadratic for, I think it was Hispanics versus non-Hispanics, right? It turned out that the best fitting quadratic for one of the groups looked like that. In other words, once you got into the heart of the real data, you had scores decreasing at an increasing rate. But for the complementary group, I think it was non-Hispanics, you had pretty much the same decline, but it was decreasing at a decreasing rate. So the best fitting quadratic was something that looked like this, right? So think about if you had two kids, both of whom had declining motivation across middle school. One's motivation was declining at an increasing rate. One's motivation was declining at an increasing rate. And you try to estimate an HLM model as a quadratic, you know, what you'd find is depends on the slope. It depends on how you scale this. If this becomes, you know, zeros back here, then you've got a slope like that for the Hispanic group and a slope like that for the non-Hispanic group. But think of what happens when you're trying to predict a quadratic, right? So this is an inverted U. So as you know, the quadratic term, if it's an inverted U, is negative. So B2 is less than 0 for this group. And this is a U-shaped, so B2 is greater than 0 for this group. So in this first level, you're estimating a big positive B2 value for one child and a big negative quadratic for the other child. And then you're plugging in both of those values into this equation and trying to make sense out of it. And you can easily have situations where their trajectories are essentially identical. One is, they're both decreasing. They're both decreasing at a similar rate. One's just a little bit more increasing at an increasing rate. The other is increasing at a decreasing rate. And you're getting these radically different quadratics fit to them, right? So I've never trusted the quadratic term in these multi-level models because they're impossible to interpret. But the more straightforward linear model does make sense. Okay, so I cleaned up the board a little bit. I took away the quadratic terms and then this third predict the quadratic equation down here. And we're back to the simple linear growth model. And so again, we're just fitting a linear function to every child. We're taking the intercept and the slope for every child and using them as dependent variables and relating them to some independent variables of interest. All right, so let's think about what the value of these equations is relative to all the other kinds of change equations and level equations that we've been talking about. Let's take this first intercept equation, right? All we're doing here is taking the intercept, which in this case is that value. It's the value of the cognitive score, that's the dependent variable here, where x equals 0. And we scaled age so that 0 age was the beginning age 5. And it's not quite what the actual observed cognitive score is, but rather it's the projection of this best fitting line to the point where it crosses this new origin, right, 0. being age 5. So all this does, this equation for the intercept, is to take this projected value of the cognitive score for age 5 and relate it to independent variables of interest. Now think about that. You're just taking scores at a single point, right? There's no information from beyond age 5 other than the best fitting slope that gets in here. This is just the initial point related to baseline variables, characteristics of the school, characteristics of the family. That's just a cross-sectional regression in effect, right? We're just, these independent variables are typically measured at baseline. Baseline is age 5. So you're just taking cognitive score at baseline, adjusted a little bit for this best fitting slope. Cognitive scores at age 5 is a function of baseline variables at age 5. You know, whoop-de-doo, you've got a cross-sectional regression, and we've talked endlessly about how susceptible cross-sectional regressions are to omitted variable bias, right? More so than most change equations. So this is just a, you know, a not very useful level equation, cross-sectional equation, relating independent variables of interest to initial cognitive scores. The slope is somewhat more interesting because that does take advantage of all the data that you've got on the child between ages 5 and 9 here. But think about what this is, right? We've estimated a slope and we're relating it to independent variables. What's the slope going to be? Well, way back to the second lecture, we saw if you've got this kind of slope, and if you rescale it a little more to -2, -1, 0, +1, +2, right? These rescalings have no effect on the slope itself. But this should look very familiar, right? Because as we talked about in the second week, an estimate of a slope is just the sum, in this case, as age goes from -2 to +2 of x1 minus, well, xi, well, let's call this t equals -2 to +2, xt minus x bar, yt minus y bar, all over the sum of xt minus x bar squared. All right, that should be familiar. That's just a simple equation for a slope. And if all you've got in this first level is just a single variable, that's a bivariate regression, cognitive scores on age. So the slope that you get, the B1 that you plug into this second equation, is exactly the same as this slope that we talked about in the second week of class. All right, and it's, if you work it out, is going to be, so if you express the x's and y's as deviations from means, right? We've already done that in the case of the x variable, but let's say you do the same thing. We're just trying to simplify this so it's just a YT, and where it's understood that Y is always a deviation from an individual child's mean Y. All we're getting is just the very familiar -2 Y -1, well, Y1 -1 Y2 +0 +1 Y4, right? This is 0 times Y3 +2 times Y5. Right, again, same as what we talked about in week 2. So this slope is really just a measure of change, where these things are negatively weighted, these things are positively weighted, where the points at the extremes, age 5 and age 9, becoming age -2 and +2, they get a double weight. And then the second and fourth observation get half that weight, and the middle observation gets no weight at all. Right? The middle observation determines the height of this line, but doesn't have anything to do with the slope. So this is just a measure of average change. Where you're measuring average yearly change with the slope. And that's fine, right? That's a nice measure of change. It's taking into account all but one of the observations that you have, and that middle observation doesn't count because it's not affecting the change itself. But think about other measures of change, right? Last time when we talked about the change models, we had change in Y as a function of, let's say, family characteristics and school characteristics. And if we apply it to these data, Y change in Y might be times Y1 plus 1 times Y5. All right, sorry, let's do it this way, right? A simple change measure. We've got Y5 minus Y1. And if we express it this way, we can see the parallels to what comes out of the first level of an HLM model. We're giving all the weight to Y1 and Y5, whereas running a regression through the whole 5 observations gives a double weight to the Y1 and Y5 relative to the weight for Y2 and Y4. So empirically, you wouldn't expect that much difference in the change measure that comes out of here and the change measure that comes out of here. And in fact, that's usually the case if you run those two kind of models. So all that we talked about in the previous class kind of carries over to these kind of models. In particular, we can now ask ourselves if this is really just a change in Y as a function of family characteristics and school characteristics. My question from last time was, what theoretical model does this correspond to? And I'm not sure what the answer is, right? Last time we talked about a couple of different conceptual models, longitudinal models, right? There was instantaneous change, which had change in y is a function of change in x, right? Instantaneous change had a kind of a cross-sectional relationship at time 1, a cross-sectional relationship at time 2, and then we took the difference, right? And that gave a model where change in y was a function of change in x. But typically, when people fit these multi-level models, there's change in y, there's the slope, but it's a function of levels of x, initial levels of x. So that's not an instantaneous change model. Maybe it's an accumulation of inputs model. Well, what did that look like? That indeed had a change in y on the left-hand side. But what was on the right-hand side, right? The accumulation of inputs model had, if you look at age, it had where someone was, let's say, at age 5. Well, let's bring up this example. Age 9, where they were as a function of everything that happened to them from birth until age 9. Maybe things that happened more recently are more heavily weighted, but it's an accumulation of everything that happened up to age 9. And then similarly at age 5, an age 5 cognitive score in this case could be understood as somehow reflecting an accumulation of inputs from birth up until age 5, right? That was the accumulation of input starting point. And then we subtracted the two, and we just got change from age 5 to 9 here as a function of, and in this case, it was D1 times the average level of inputs between the two measurements of y. Right, so in the NICHD paper example, it was change in a cognitive score as a function of average child between ages 3 and 54 months was a function of the average quality level of childcare between age 3 and 54 months, right? So whatever our key independent variable is, maybe it's some sort of school characteristic. You've got a measure of the credentials of teachers. Do they have master's degree? Do they have certification? And if this is going from kindergarten to age to 5th grade, then the key independent variable would be the kind of average certification level of the teachers that the child had between those 2 points, or the average measure of teacher quality, the average of gifted and talented classes, the average of dual language immersion classes that they might have had, how many did they have between those 2 points. But that's a very different equation too, right? So the accumulation of inputs has a change in y, but the x isn't just initial x, it's the average level of x between the 2 points. So the slope equation isn't accumulation of inputs either, because it does have indeed a change in y, right, as measured by the slope of the line. But it's typically taken to be a function of initial conditions in the family and the school. So, maybe maybe there is a conceptual model that makes a lot of sense for that, but I'm hard pressed to see what it is. But let me know, and I'd be glad to talk about conceptual models that might make sense. So it's really hard for me to get enthusiastic about these latent growth models. It's an example where it's this kind of fancy technique, and people say, oh, I've got longitudinal data, let me fit it with a latent growth model. And so they go fit it with a latent growth model. And I've reviewed a lot of these papers, and typically they find their key independent variable of interest is significant in the intercept equation, but not significant in the growth equation, the slope equation. And they go on and on about, well, we did find a significant relationship between our key independent variable and the initial level of whatever it is. But as we said before, that's just a cross-sectional regression, right? And it's subject to all the kind of biases that happen for cross-sectional regressions. And the fact that you've got all this wonderful longitudinal data and don't use it for the intercept, and then make a big deal out of the fact that you've got a significant predictor of intercept, which is really just a cross-sectional relationship. That's not much of an accomplishment. It's usually a step backward. And the fact that things are not significant in the slope equation, which they often aren't, is kind of minimized relative to, oh, look, this latent growth approach gave us the significant result. So, I hate to be so pessimistic about this, but I'd welcome discussion when we have a chance to meet again. Let me make one more point about this, and I will, let me pause and we'll start up again. All right, so let me continue my rant about multi-level models. This is a nice example of a study that a former graduate student here did, Anna Auger. She was looking at the relationship between academic stimulation in the home. This is the NICHD data set. There's a nice measure of home environmental quality for the child that includes emotional support, academic stimulation, and so forth. So they consistently measured the academic stimulation in the home before school entry. And she composed a measure of academic stimulation between ages 3 and 5. She controlled, the equation was cognitive score, and then she had a version of this at 5, at 8, at 15. There were a couple other points. Is some function of academic stimulation in the home, ages 3 to 5, plus B2 cognitive score at age 3. Right, so it's a lag-dependent variable model. This cognitive score, then plus other stuff. She was able to control for cognitive functioning at age 3, so that kind of takes care of everything. This is a accumulation of inputs model. It takes care of everything up to age 3. It controls for age 3. So it's estimating an association between academic stimulation after that age 3 measurement on cognitive scores at various points. And it was a pretty remarkable set of associations. So here we're looking at impacts. We're not looking at age is just the age at which the impact is measured. So maybe I should, the impact at age 5 was, some significant level. The quote unquote impact, this association, adjusted association at age 8 was almost as high, and the association at age 15 was almost as high. All right, so it's a pretty remarkable pattern. And the way she wrote the paper initially was to do, exactly this kind of presentation. There was a regression result for age 5, a regression result for age 8, a regression result for age 15. And she showed that on every single occasion, the coefficient on academic stimulation between ages 3 and 5 was statistically significant and substantively substantial. It seems like a very transparent way of presenting these results. But what the referee said is, oh, you've got longitudinal data, why don't you estimate a latent growth model? All right, so do the conversion of age 5 becomes 0, age 8 becomes 3, age 15 becomes 10, right? We're just subtracting 5 from all these things. And if you're looking at impacts, the actual pattern declined a bit, but not very much. And what's a latent growth model going to look like? It's going to have a slight negative slope. This is going to be the intercept. All right, so the intercept equation is going to be pretty close to age 5 cognitive functioning, not cognitive function, but impact. It's not the actual amount, it's the projection of this line, but in this case, it's very close as a function of academic stimulation between ages 3 and 5, right? So, that's essentially what you get if you just take age 5 cognitive scores and regress them on academic stimulation, control for prior cognitive score, and put in other independent variables. But what about the slope? Well, the slope, if these are declining a bit, is going to be a little negative. And, that's fine. That's what the result is. But when you present the results in the context of latent growth model, it looks like academic stimulation has a big positive impact on initial school entry cognitive scores, which is true, but then a negative impact on slope. Now, if you really understand what's going on, that's fine. You might want to ask, is that negative slope, how much does that negative slope actually reduce the impact by the time you get out to age 15? And if this is the scenario, the answer is not much. But the mere fact that the slope isn't very negative, canceling out whatever initial impact there was, that would be the fade out example, is remarkable, right? And a 0 slope, let's say early cognitive stimulation predicted, a big initial difference at age 5, and then a 0 slope after that. that story would be remarkable. It would be that the fact that this initial impact was maintained, right, all the way out to age 15. And again, if people really understood what the model was telling us, they'd say that's remarkable. But what they see when they see the results is just a big positive impact in the intercept equation, and then kind of an insignificant negative impact on the slope equation. And they go, oh, negative, but it's very insignificant, so it's really not important for the slope. When in fact, a zero slope is an absolutely remarkable result, that there's no fade out from preschool academic stimulation. So it was, she was in the situation, if she went ahead and just published that, it's going to be misunderstood because no one really understands what these latent growth models all are about. You know, she thought of what if you made age 15 the 0 point, right? And this -7 and this -10. You could do that. And then the intercept equation would be a significant age 15 impact. And the slope would be negative, right? Which would be, I mean, the big story in all this is that age 15 still shows an impact, an association with academic stimulation. That's an incredible result. And scoring this as 0 would at least give you an intercept equation that highlighted that point. But you know, it would also be accompanied by a negative slope, which if people understood, you know, they would understand that that is a little bit smaller than what it was 10 years before. But the way she originally wrote the paper was to have separate equations for age 5, age 8, and age 15. And what could be clearer than seeing this coefficient quite large at age 5, almost as large at age 8, and almost as large at age 15, right? That told the story in such a transparent way. And the referee saying, oh, you've got longitudinal data, you need to estimate a latent growth model, just obscured the whole thing. All right, so end of rant. Let me talk just very briefly about the SEM version of this. All right, so I've changed things up a bit. We're now switching on latent growth models from the multi-level style to the SEM style. So this won't take long because it's just a way of doing the same thing that the multi-level model did with SEM. And here, just to make it a little bit easier, instead of 5 observations, let's suppose we've got 3 observations. And the trick here is to think of an intercept factor and a slope factor. All right, so just as the multi-level case, we've got an intercept model and then the slope model. And to construct these factors, we estimate a model where instead of having these paths free to take on whatever value they want to take on, you constrain this path to be 1, this path to be 1, and this path to be 1. And then with that's the intercept factor. And the slope factor, you have this first slope factor be 1. This slope factor you constrain to equal 2. And this path from the slope factor constrained to be 3. So the point here is to end up with a slope and intercept scores that you can then use in the context of a model that might be of interest. So the slope you want to increase by whatever interval there is here, and the intercept you want to keep things constant. So let me just pull up an example here. All right, so this is exactly this latent growth model that I talked about. We've got time 1, time 2, times 3, the intercept factor 1.0, 1.0, 1.0, the slope factor, oh, in this case it's 0, 1, and 2. Could be 1, 2, and 3, which is the way I had it. But the point here is then to use this and embed it in some kind of fancier model, right? So with the multi-level model, we didn't just want to come up with a slope and an intercept for everybody. We wanted to predict those. And this model is of the reciprocal relationships between adolescent alcohol use across the top, and then peer alcohol use across the bottom. So it's a longitudinal study. You've got 3 measures of alcohol use, time 1, time 2, time 3. And then you also have reports from those same kids of alcohol use of their peers, time 1, time 2, time 3. So what they did was to have an intercept for adolescent alcohol use, and then a slope for alcohol use. And those came from constraining these coefficients to be 1 and these coefficients to be 0, 1, and 2. So that gave you, in effect, the same kind of intercept and the same kind of slope that you got from the multi-level model. In this case, they were interested in the reciprocal relationships between adolescent alcohol use and peer use. So you've got these 3 measures of peer use, and you do the same thing. You've got an intercept, you have a slope, you estimate the intercept value with paths of 1, and the slope with paths of 1, 2, and 3. And what you get, controlling in this case for age and gender and parental alcohol status, those are the only control variables. And the key paths here were, to what extent does subsequent peer growth in alcohol depend on initial adolescent alcohol use? And then by the same token, to what extent does the adolescent's own growth in alcohol depend on where peers began? Right. So, not surprisingly, this path is 0.18 and significant, which suggests that your trajectory of alcohol use is a function of how much alcohol your peers used at time 1. This is a little strange. It's saying your peer alcohol trajectory, it's a negative coefficient. The slope is less the more you yourself used alcohol. But I don't want to talk about the substance of this. I can give you a reference if you want. But the point is that this is another way of using latent growth modeling in this case, a fairly sophisticated way where you've got two intercept and growth factors, two different kinds of variables, and you stick them into a model for evaluating the impact of those two. All right, so that ends the whirlwind tour of latent growth models. I'd be glad to follow up if people have interest. There are follow-on courses to the applied regression that go over these, and it's good that someone else is teaching them and not me. Not a big fan of these, but you know, they especially for this more sophisticated example, it's kind of an interesting application of these latent growth models. But you know, I'm singing the same song when I worry about emitted variable bias with these models, but especially with the slope equations. I'm wondering what conceptual model are you really estimating when you estimate these change as a function of initial level models. Okay, so see you in class soon.